esse colóquio vai ser gravado, vai ser no YouTube, na oficina do departamento. Se você faz perguntas, você consente que você vai ser, a sua voz vai ser gravada também. Bem-vindos. É o primeiro colóquio, né? Temos a honra e o prazer de ter o Chun Shen. Ele se formou na Universidade de Jiatong, em Xangai, e depois fez doutorado na Ohio State University. Alguns de vocês trabalham lá com furicais. Depois fiz postdoc na Universidade de McGill, no Brookhaven National Lab, o laboratório do Rick. E agora ele é professor na Wayne State University, em Michigan. É um dos grandes expertos do mundo da simulação numérica do fluido ideal, perto do ideal, que é feito nas colisões de íons pesados. É o código que é usado na simulação. Ele é um dos autores que fez isso. Então, eu vou falar do trabalho dele. Please, go ahead.
Okay, thanks for the introduction. So today I will talk about basically the state of art or the frontier of the heavy ion physics, and where we are and where we're going forward from now. So let me start my talk with the standard or basics phase of matter that we know from our daily life. So we know that we have knowledge about the matter being formed in solid, liquid, and gas. And also we know that as the temperature heats up, we will have also a phase called plasma phase, which usually lives in the center of the sun, where electrons are set free from the nuclei, and they can actually exhibit some different emergent phenomena compared to the other phase in this temperature. So today I want to go one more extreme, and we know that atom is composed by electrons and also the central nucleus, and the nucleus is composed by proton and neutrons, and inside the proton and neutrons we have the fundamental particles called quarks and gluons, which are the fundamental building blocks for the nucleons. And they exist only in the size of about 10 to 15 meters in terms of the spatial extensions. So we can ask the questions, what if we heat up the systems further, like just strip the nuclear electrons from the atom? Can we strip off free quarks from inside the nuclei and form something like plasma, like with the quarks and gluon degree of freedom? The answer for that is not that easy because of the color confinement. Because the potentials between quarks and gluons actually increase linearly at a longer distance. So if you want to kind of pull one of the quark out from the nucleon or proton, the input energies will be a lot more, and at a certain point it will actually reach the threshold to produce a new pair of quark and antiquark from the vacuum. So in the end, you end up basically with two hadrons. Both are color neutrals, and they are both compound states of quarks and gluons inside. So then in this case, in the traditional kind of pictures, the quarks and gluons never reveal their own degrees of freedoms in nature. However, from the first principle calculation, you find that at a certain temperature, so-called Tc, which is some critical temperature, you can see that the long-distance potentials start to melt and then become kind of flat, like the Coulomb or spring Coulomb potentials at a slightly higher temperature. This means that there is kind of a hope that with certain temperature, when you reach certain temperature for this nuclear matter, you can actually kind of reduce these long-range interactions, and then you can set free the quarks and gluons in these high-temperature systems. So another way to understand this is kind of in the vacuum state, you have basically string-like kind of potentials between the two quarks from each other, and they increase linearly, and so that you have the confinement. And if you have a high temperature where you have a thermal bath between this quark, and then the thermal bath can introduce some random kicks and kind of screen out the long-range string potentials, and then at a certain point you can have a soup of quarks and gluons at certain these high temperature things. And that's basically the phase we are looking after, and we want to try to basically analyze the property of the matter in these kind of extreme conditions. Such kind of transition temperature can be calculated from first principle of the strong interactions called quantum chromodynamics. And what you find is that the system's degrees of freedom has a rapid increase at the temperature around, say, 200 mega electron volts. And you can see that the degree of freedom increases about from 10 to about 50 in this narrow temperature window. And if you want to translate this mega electron volts unit from high energy physics used to the normal Kelvin, you can have this pocket formula that 1 MeV is about 10 to the 4 Kelvin, and 1 mega electron volts is 10 to the 10 Kelvin. So 200 MeV is about 10 to the 12 Kelvin, which is about trillion degrees temperature. And this temperature is really high compared to, for example, the center temperature of the core of the sun, which is only 10 to the 7 Kelvin. So this is about 5 order magnitude hotter than the center of the sun. So this is really hot temperature. And also you can translate this temperature into some kind of pressure estimate for the system. And you find that in normal units, like in terms of atmosphere pressure, this is 10 to the 30th times of atmosphere pressure. So this is really high temperature, high pressure environment, which is extreme. And in this cartoon, you can think about is that in the normal phase, we have nucleon with distinguished boundaries between each other. And if we increase the pressure to be so large, it's kind of to squeeze everything together. And in the boundary between the nucleons start to kind of hard to distinguish from each other. And then basically you have form a super Quark-Gluons in a kind of relatively larger distance. And then in this type of phase, the theory suggests that you start to see degrees of freedom from quarks and gluons kind of away from the hadrons. However, also you can see that the limit of the Stefan Boltzmann non-interactive gas of quarks and gluons are actually at this dash line. So they're still about 1/4 away from the actual free quarks and gluons limits in the extreme high temperature. So this means that we start to see the degrees of freedom from quarks and gluons, and but they could be also strong coupled. So these extreme conditions, like trillion degree Kelvin, now 10 to the 30 power times of the pressure, only exist in the very early stage of the universe, about a few microseconds after the Big Bang, and much earlier than the first life that can be detected, which is 3 times 10 to the 5 years after the Big Bang. So understand the properties of these Quark-Gluon matters in these extreme conditions can also help us to see what the early universe looks like in terms of strong interactions at this early stage. And how do we do this analysis? Because this is actually in the universe, this is already long gone, and also the first thing that we can detect lights from the universe is only very kind of later time from there. We need to recreate such conditions in particle accelerators. So we cannot create a microscopic size of such conditions, but through particle accelerations, we can actually accelerate heavy nuclei in these accelerators and create such conditions at a short time scale. So the 2 main facilities in the world that can do these heavy ion collisions are one so-called relativist heavy ion collider at the Brookhaven National Lab at New York in the US, and also a larger version of that is at CERN called Large Hadron Collider. And the circumstance is much bigger in the European version, and the collision energy is about 25 times higher at the LHC compared to the The cartoonish kind of pictures of doing heavy ion collisions look like this. So we have 2 nuclei coming in, kind of they first accelerate to near speed of light. So we know that from special relativities, if we kind of observe in the left frame, they look like 2 pancakes kind of flying towards each other due to Lorentz contractions. And after the collisions, there's a very tight interaction zones, which we hope the system can be squeezed and create extreme conditions like can create Quark-Gluon Plasma. And as the system falling apart, the system will fall back into hadrons and we can measure afterward. So here's a kind of more realistic numerical simulations you can simulate from kind of a computational model. So here, the right and the blue dots are basically the incoming nuclei for two nucleons inside the two gold nucleus. The blue ones will basically fly in these negative z directions, and then the red will fly towards positive directions. They first basically overlap with each other, and then we find that there's a dense hadronic fluid phase actually created. And then as the system falling apart, those fluid cells will basically fly back into hadrons, which is pointed as these white dots, which can be actually detected in the detectors. So this is kind of the underlying pictures what we think a dynamic evolution of one heavy ion collisions looks like, and we want to analyze this together with experimental data. And this multi-particle emissions is not just from simulations. You can actually detect those hadrons as tracks in the Hadron Collider. So this is one of the lead-lead collisions, only one collision of lead nucleon, one lead nucleon, and then basically produce thousands or 10,000 charged tracks that can be recorded in the detectors. So that's basically how violent one of the heavy ion collisions look like, and you really convert the incoming kinetic energy of the two lead nuclei into basically new particles in these collisions. And also, when you look at these 10,000-ish particles in these systems, you start to think, okay, you can try to apply traditional statistical mechanical physics tools to understand the system as a microscopic systems in terms of how the energy and particle, in terms of particle flows through the systems. So, as similar to the many body systems, when you reach so many particles, you will start to see emergent phenomena. So this is very like kind of if you look at a stool of bird on the sky, they will actually fly in very intriguing patterns, or kind of school of fish in the river, or even if you look at the bicycle race, if you look at a microscopic shape, they form in some kind of intriguing shape, which you usually call emergent phenomena through kind of fundamental interaction between particles. So what we want to ask is, in these many-body nuclear systems, where we have degrees of freedom from quarks and gluons, what type of many-body emergent phenomena will arise from these interesting systems? So in our field, we found actually this is a really fascinating system to study because it has a really high temperature, about 1 trillion degrees Kelvin. It's really actually small in terms of size of nucleon, but also exhibits really surprising behavior in terms of fluid. It has a very small share in all viscosities, and also it can actually have the largest vorticity that can be ever measured in the collisions happens. So here basically is kind of a picture that in the public you still see that if you look at the viscosities kind of constrained in Quark-Gluon Plasma, the minimum value is usually much smaller than the regular fluid we know, like waters, liquid helium, even some cold atom systems where it's really strongly coupled. And this is kind of the system part of the reason why we want to study this Quark-Gluon Plasma properties, because it actually exhibits really near perfect fluidities in such high temperatures. Also, there's recent measurements by Rick Starr, which kind of also look at the vertical kind of aspects of these systems in off-equilibrium center, where system has finite angular momentums. And we find also these kind of large vertical structures also happen in systems. The theoretical question underlying is how to understand this amazing emerging phenomena from kind of QCD interaction between quarks and gluons. So that's kind of one of the big questions we want to solve in our field, try to kind of understand how these many-body kind of effects arises from the fundamental interactions. So as I said, that the studying heavy ion collisions is not easy because it has really kind of challenging conditions. First of all, as the system goes through this certain stage, multi-stage evolution dynamics, the things happens really fast. For example, as the system start to collide with each other, it goes through some pre-equilibrium stage where system evolve from far out of equilibrium status to some kind of near equilibrium where you can start to think about a hydrodynamic description of systems as it passes through the Quark-Gluon Plasma phase to hydrogen gas phase and eventually freeze out at a later time. What we find is that the interesting dynamics happens on the time scale of a few 10 times 10 to the minus 3, 23 seconds. This actually is usually called a few yoctoseconds. So if you compare this time scale with the fastest time scale from lasers that you can make, the laser pulse is minus 10 to the 18. So this is still about 6 orders of magnitude shorter than the ultra-fast laser we can make humanly in the current status. And also the system is tiny, so it's basically the size of the nucleus, which is about 10 to 14 meters. So this tiny size of the collision system and ultra-fast dynamics pose a very challenge kind of difficulties to actually detect the dynamics of the Quark-Gluon plasma at these early stage explosions through experimental kind of method. We cannot kind of see them or kind of detect them with some kind of external probe. But there's also a flip side. So basically, we look at the product of these collisions. We have seen that there's many different species of hadrons produced, basically due to the conversion of energies from the incoming beam energies into created new particles. And also, you have different flavors of probes, like photons, dileptons, or other QCD probes produced in here. So this actually really looking at a different kind of product of these heavy-ion collisions. You can actually try to understand different aspects of the Quark-Gluon plasma through the property of these different types of particles. And by this type of analysis is very similar to the multi-messenger analysis in the astronomy, but I will say that in heavy-ion physics, we start from day one by looking at the different nature of particles together. We are always doing a multi-messenger analysis to understand the property of the Quark-Gluon plasma at early stage. So just to get this more concrete, so in heavy-ion physics, we detect different types of hadrons, which can be kind of categorized into these 4 different levels. So firstly, we have majority of the hadrons produced as these tracks that measure in the detector. So they are basically kind of low transverse momentums, but they actually usually we call bulk evolution, bulk particles emissions. On the top of that, we have rare probes like high energy jets, which act as a spray of particle that has deposited energies in this well localized phase space. And they basically serve as a color probe to basically interact with the produced QCD bulk medium. And then you can measure the energy for different types of systems and looking at how the medium modify the structure of those jets as they go through the medium. In addition to this colored probes, we also have colorless probes like electromagnetic radiations from basically thermal body, black body radiation, because if the system has reached about 1 trillion degree Kelvin, if you think about it as a black body system, it will certainly radiate photons and leptons. And because those photons and leptons only interact with systems through electromagnetic radiation, which is much weaker compared to the strong interactions, they basically will carry much cleaner information at their burst point compared to the majority of the strong force. And the last but not least, we also have electroweak bosons can be produced at very early stage of the collisions, and then they will travel through the system without interactions and give us information about early stage. So really that in heavy-ion collisions, by looking at all these different types of observables together, we can know about the collectivities and also early stage of the evolutions in one systems. And also by utilizing all this experimental data, we also need to build kind of unified theoretical framework to actually calculate all these observables in one of these comprehensive kind of setup. And the JETSCAPE collaborations that formed in the US that has been basically one of the main driving force to basically build up such kind of computational tools that can be benefit for the high energy nuclear physics community to actually simulate all these different type of observables in one kind of event generator, so that you can actually study all different type of correlation between all these different particles in one of the simulation environment. So the ultimate goal in our case is basically try to look at, say, the observables that measured in different aspects, and then to kind of map back into the property of the Quark-Gluon plasma. And we want to basically do this not only at the Large Hadron Collider, but also at multiple kind of heavy ion facility in the current and future kind of setup. So you would like to see that the case is that if we measure certain observables, it will actually give us certain aspect of constraints of the QGP. So this kind of linear mapping can actually be easy for us to actually connect different observables with properties. However, the connection is not so clean. So usually you will have facing a very complex inverse kind of mapping problem from how you want to look at the experimental observables and how they kind of can help you to constrain the property of the Quark-Gluon Plasma. Trying to carry out this inverse problem from using the experimental data to constrain these multiple aspects of the Quark-Gluon Plasma is actually a kind of a very computational intense problem, and they're facing about exascale computing in the current stage. So let me probably now dive into a little bit more ingredients about this kind of the theoretical frameworks that were built up to simulate heavy ion collisions and talk about how we basically try to extract useful information of Quark-Gluon Plasma through data to model comparisons. So in heavy ion collisions, as the system evolves, we basically separate the system into three major kind of phases. So the initial phase will have some kind of initial state of the two nuclei coming in, and then going through some pre-equilibrium stage where you can model the dynamical evolution of the energy momentum tensor. And then about one Fermi over C, the energy momentum tensor can be very like a hydrodynamic equation of motion. So then you can kind of switch to hydrodynamic evolutions. And then later on, when the density becomes really low, you can translate to a hadronic transport, where a transport description where you can model the dilute systems through kind of Boltzmann equations. The key idea is that we build up these hybrid simulations, and this is mainly kind of trying to connect continuously the evolution of energy momentum tensor as a function of time. So what we really look at is the dynamical evolution of the systems and how the energy momentum tensor evolves as a system goes. On top of that, we have, as I said, we have real probes like quarks and gluons that can form jets, also radiate photons. So from these bulk mediums, like have a certain well-defined temperature and flow velocities, we can calculate the thermal photon radiations as well as photon energy loss in this color phase. And then they basically serve as real probes for this Quark-Gluon Plasma, in addition to the bulk evolutions. So the main workforce for this bulk evolution that employed in these simulations is so-called hydrodynamics. So you can think about hydrodynamics as a long-wave kind of effective description of a strongly coupled systems. The building block of hydrodynamics really depend on just two fundamental inputs. One is just equation motion. You're trying to solve the conservation law of energy momentum currents as well as conserve charges. And need to solve this with different type of systems by specifying the fluid as a equation state. So you can think about the hydrodynamics as a very successful theory to be applied to the star formation dynamics, also help you to design the race car in the kind of regular size of the daily life size of physics, and also use the relativistic version of hydrodynamics in terms of simulating the dynamics of Quark-Gluon Plasma in heavy ion collisions. And in this case, we need a relativistic special relativity because all the particles are flying close to the speed of light. What we found is that if we want to include off-equilibrium corrections, for example, shear and ball viscosity, in this relativistic formulation of hydrodynamics, it's not that trivial, and very easily you can violate causalities from direct generalization of state Navier-Stokes equations that apply really well from the daily kind of our daily life. So our field is actually leading the formulation of a causal relativistic hydrodynamics to be actually applied to these small collision systems in the general hydrodynamic theories. So hydrodynamics, in a nutshell, can be basically summarized in terms of this equation, where you can see at the left-hand side, essentially you can interpret as a time derivative of flow velocity, which essentially is the accelerations in my fluid cells. As you can interpret this equation by Newton's second law, the acceleration is equal to a force divided by its moment of inertia. So in hydrodynamic system, the force is basically coming from a thermal force, which is the gradients or spatial gradient of the local pressures. And the moment of inertia for my fluid cell essentially is the system's enthalpy, which is energy density plus pressure. So this equation of motion essentially tells you that the local acceleration is driven by the pressure gradients, which act as a thermal force. So on the right-hand side, as you can see that this is one of the hydrodynamic simulations with basically the color coding with the thermal pressures. As you can see that the pressure in the center is basically hottest and then basically generate a push to the fluid cell and accelerate outward radially as system evolves. So this is the takeaway from hydrodynamics I want you to remember is essentially it's just a translator to translate the initial spatial inhomogeneity of your medium into a fluid motions like flow velocities. And eventually this can be mapped into the momentum content of the particles and can be detected in the particle contents. Another thing I want to point out is this strongly coupled fluid dynamic behavior is not unique in heavy ion collision at high temperature. So if you look at, say, cold atom systems that is extremely cold, and if you prepare the initial state at the cigar shape of the configurations, you initially will have a transverse kind of pressure to be much larger than the vertical one. Then you can see that as time progresses, the shape changes and they will generate a much faster transverse expansions compared to longitudinal directions. And this is very similar to the numerical simulation done in heavy ion collisions, where if you start with almond-shaped overlapping regions, you will generate more flow in the horizontal direction than the vertical directions. The thing I want to point out is although you can see the qualitative hydrodynamic behavior is similar between these two systems, but they are very completely different because one is almost at 0 degree Kelvin, and the other is at about trillion degree Kelvin. And time scale for the evolutions happens also at vast different time scale. One happens at several hundred microseconds, and the other happens at the octosecond, which is 10 to the minus 24, or 26, 24 seconds. So you can see that the hydrodynamic behavior happens to be similar, but also there's a concrete, very large different kind of scales happens in these systems. So one thing I want to address is trying to understand, say, the property of the transport property of Quark-Gluon Plasma, for example, shear viscosity. So the shear viscosity, you can intuitively understand it as is a resistance to the shape deformations of the flow distributions. For example, if you have a shear field, you want to change the kind of the shape of the things like this, then the shear viscosity is act as resistance to do it. So you can, in the simulation, what you can actually simulate is kind of identical systems, but with without free viscosity to demonstrate the effects of shear viscosity. So here we have one nuclei going inward, indicated as the yellow contour, and then the other one going out of the border is the purple one, and the interaction zone is actually overlap here. So the red dots kind of indicate the initial energy density distributions from these collisions. So as you see it evolve this energy density profile with and without shear viscosity, at the late time you can clearly see that with the viscosity to try to smear out the densities much smoother compared to with viscosity, without viscosity. So without viscosity, you can still see some concrete structures in my density field that are still present at the late stage. However, the viscosity is trying to wash out this flow difference and make the things more homogeneous. So this actually is one of the imprints of the effects of shear viscosity in these flow dynamic measurements. And then we want to basically try to look at what is the impact of smearing out this flow velocity in the final state of observables and try to link it into observables. So in observable, we want to measure is every collisions. So that you will see is that in the detector, you will have this energy depositions, which is indicated as the red and blue towers in the parameters of the collisions in the transverse plane of the collision. And you can get basically a particle counts as a function of the azimuthal angle of the detector looking at this. This is like a wavenet. And we all know that with these angular distributions, you can actually do a Fourier transform to basically convert this information into basically Fourier coefficients. So by performing Fourier transform for this kind of analysis, you can get the so-called VN coefficients in our field, which is called anisotropic flow coefficients. And they basically capture kind of dipole deformations in these distributions, or elliptical triangle distributions, or kind of in these angular distributions. One of the things that can be connected to other field is that this anisotropic flow is basically a consequence of propagating initial state fluctuations through hydrodynamics with viscous effects, and then basically can measure kind of power spectrum of this anisotropic flow in the final state of particles. And this is a very similar analysis compared to the power spectrum analysis of the cosmic microwave background, that you also look at power spectrum fluctuations of the temperature fluctuations. But in our case, so in the CMB, you can actually go to very high moments like 2,500. But in our case, usually the signal stamps very fast. And the current state of art is measured by Alice, can actually measure the harmonic order of these transport coefficient, of these anisotropic flow coefficients up to n equals 9 for these centralities. Also, you can see that this sharp drop in these spectrums, which essentially is related to viscosity, basically we'll see that the higher viscosity, the more finer detail will be washed out. That's why this is dropped. And also interestingly, the data also suggests that at order 9, in this 40 to 50 centrality range, you could have some monotonic peaks at the higher orders, which represent maybe the acoustic peak at this point. So by basically using these measurements, we can now kind of doing this inverse, try to carry out this inverse program, try to use the experimental observable to constrain the properties of the Quark-Gluon plasma. So here is basically one of the calculations carried out by the JETSCAPE collaboration a few years ago, try to understand what is the value of shear and ball viscosity of QGP that can be kind of constrained using the observables on the left-hand side. What you can see is they carry out this so-called Bayesian analysis, which is a multi-observable, multi-parameter constraint, and it will constrain allow the value of shear viscosity from the gray to the orange value. So the orange value is the final constraint value, and the initial value without constraint is indicated as the gray band. So what you find is that the data measured by the RIC and RC measurements can actually help you to constrain the shear viscosity value between 0.25 to 0.25 GeVs in this region, and the viscosity value is about 0.1 in the units of megaton/kV. So, and also you get some constraint about ball viscosity in the low temperature, and the high temperature essentially you can see that there's not enough constraint from the current molecular uncertainties. So that means that the precision data that can be measured in the current RIC and C measurements can help us to understand at least the property of the Quark-Gluon plasma near this phase transition between the hadron and the QGP phase. And also you can carry out additional calculations, for example, extracting kind of how the high energy partons interact with the medians of the transport coefficients is usually characterized by this Q hat, which is the average momentum transfer of a high energy partons as it travels through the median. So the value for that is basically around 8 in terms of temperature Q. So this is also something that we can use to use the high temperature or high energy kind of jets to actually extract the interaction between high energy parton and the median from these JETSCAPE status. So far, what I talk about is essentially what we found is the Quark-Gluon plasma has really small viscosities, about 0.1 in units of H/kV around transition temperatures. And really what to do in the near forward is basically trying to understand this emergent fluid behavior through looking at the different aspects of collisions. So in our field, there are 3 kind of main directions to this theory and experiments are going forward. One is trying to understand the inner working of QGP, like what is the degrees of freedom of the building block at the high temperature of this Quark-Gluon plasma by using multi-resolution scale probes like QCD jets, heavy pots and EM probes together. And by varying the energy of the jets, etc., you can probably look at different resolution scales at the QGPs. And second is a very interesting question is what will be the limit of the smallest Quark-Gluon plasma droplet, as you can experimentally shrink the size of the collision object, and then see whether when that does the collective behavior disappear from the experimental measurements. Certainly, if you can actually experimentally control the collision energies, try to basically control how much incoming baryon can be stopped in the collisions, we can use this as effective doping of the baryon density into the fluid and study the phase structure of the Quark-Gluon of the QCD at the finite temperature and finite chemical potentials. So all of these are kind of very kind of a large kind of framework, and each of them will basically deserve a separate seminar by itself. So today I basically will just highlight in one direction, which is the second one, which will be basically try to shrink, kind of give you a story about shrinking the QGP size, and then see whether there's a limit of Quark-Gluon plasma in this QGP droplet. So the simulation can be done in this way. So basically, in heavy ion collisions, you can collide the largest heavy ions with like uranium, and then you can shrink it close to like say oxygen, like xenon, oxygens, even to proton-proton collisions. So in this case, you can experimentally kind of control the incoming size of the nuclei, and then shrink the size of the produced matter's initial state, and then basically try to shrink the droplets of the QGPs. And then you can also look at the flow measurements of this all different type of system, and plot as a function of the particle numbers that produce in the final state. And the left-hand side is RIC, C energies, and the right-hand side is RIC. So the kind of the qualitative takeaway is that if you just apply hydrodynamic model with a single parameter sense, you can qualitatively capture all the flow degrees of freedom or kind of behavior as you go from large systems to small systems. And that's really kind of intriguing, that you can somehow there's no limit of the how small system can be to be collective in this type of studies. But let me basically give you a journey to kind of try to shrink from large system to small system one by one, and then tell you that there are some interesting kind of connections we found recently that can be connected to other fields. The first is that, as I said, so the hydrodynamics behave really kind of a very effective translation between a initial spatial geometry into final state. For example, if you start with a small or large compact or not compact fireballs, it will imprint into small or large radial flow in the final state and imprint into the transverse momentum you measure in the final state particles. Also, you have seen that if we translate this cigar-shaped initial state, it will give us elliptic flow measurement kind of generation in the final state. And also, if the system looks more triangular, it will give us a triangular flow like V3 kind of in the final state. So this also all just tell you that hydrodynamics is a very effective theory to translate the initial shape and the size of the Quark-Gluon plasma to experimental measurements. On the other hand, so if we use the experimental measurement data, we can try to infer the initial shape and size of Quark-Gluon plasma, and eventually the initial common nucleus. So we know that in heavy ion setup, if we want to know the shape of heavy ions in the initial state or its ground states, usually it's kind of illustrated by parameterize it in terms of Lou-Saxon distributions, where this R can be basically dependent on the angles. So that basically introduced kind of a so-called deformation for nuclei. So for example, for uranium, if we know that it has elliptical nuclei shape, then you can put in a non-zero beta 2 parameters to describe the elliptical shape of the nuclei. And you can also do it for higher order deformation like triangle and these quadrangular formations. For the second order transformation, you can also assume that the three axes of this elliptical shape are not all equal to each other, and these usually is called triaxialities in this elliptical form. So usually in the low energy experiment, either low energy nuclear physics. So this is usually called intrinsic frame, so an intrinsic shape that people parameterize this Lou-Saxon potential and try to minimize kind of the wave function energies. And eventually you will kind of project out all these shapes in the ground state, so the ground state is always kind of round. But in heavy ion conditions, we kind of interpret these deformations as basically multi-particle correlations event by event. So every event, you may have kind of fluctuation of this elliptical form that can be detected as an initial in heavy ion collisions, and then this will propagate through the heavy evolutions. So we can see some kind of multi-particle correlations as an influence of this intrinsic shape deformations. So here is one of the examples that we can compare by studying different system size. So here we're studying the flow difference between the lab collision, which is a larger system, compared to an intermediate size system, which is neon plus neons. So neon has a nuclear number, which is 129, which is smaller than 208. So on the left-hand side, I plot the ratio of this elliptic flow between these two systems and the function of collision centralities. The collision centrality means that in zero centrality, you have almost head-on collisions. So you almost have two nuclei almost fully overlap with each other. And the shape of the produced Quark-Gluon plasma will basically reflect the shape of the incoming nuclei. As you go to peripheral collisions, they basically will have large impact parameter, and then the impact parameter determine the unknown shape in the between. So what we want to focus on is basically these central collisions where you can probe the initial geometry of the nuclei. On the left-hand side, we do the simulation for this ratio with different final state effects in hydrodynamic setup, and then you can see all the curve collapse into one. So this means that although the two systems has two different sizes, if you take the ratio of the elliptic flow, all the hydro influence on this observable will be basically cancel out by looking at the ratios. And this ratio is only sensitive to the initial input of my shape of my xenon nuclei. So if I change the electrical deformation of my xenon nuclei by just amount from 0 to 0.1516 to 0.2, we can see that in the central collisions we zoom in, you will have a really large variations of this beta 2 kind of signal for these V2 ratios to be correlated with this. And this means that by basically measuring this ratio in the experiment, you can actually constrain the deformation, the beta 2 deformation of this xenon nuclei in experiments. And this actually provides a comprehensive or complementary measurements compared to low energies and even the high energy when you destroy the xenon nuclei, the shape of the Quark-Gluon plasma, remember the beta 2 deformation, and give you still the information from these flow patterns. Now we can go to a little bit lighter. So from xenon, we go to basically lighter nuclei like oxygens or neon, which only has about 20 nucleons in one side. So these actual experiments can be actually realized in the recent so-called actually small fixed height experiments, where you have a lab beam coming from the accelerator, but the other target is basically a gas chamber where you can input a noble gas in. So if you think about neon, which is neon 20, which is about 20 nuclei, you can think about 5 alpha clusters. So you can have 4 alpha clusters like tetrahedrals, and then 1 alpha cluster above. So this really looks like a bowling pin shape for neon. So if you think about neon lead collisions, a lead colliding with neon, this is really like a bowling ball setup. But this is a kind of really cool setup in the high energy experiments is because the lead is relativistic. You have a relativistic bowling ball alleys by colliding lead with neons. And what we found is that if you compare lead neon versus lead oxygen, where basically you have one less alpha cluster, just 4 alpha clusters for oxygens. In the central collisions, the lead essentially serves as a wall and basically imprint the shape of lead nuclei into your QGP formations. So your QGP essentially just looking at the shape of the neon versus oxygens in the central collisions. And if you do the hydrodynamic simulation and make the ratio between these two systems, you find that neon systems versus lead, neon will give you about 20% more elliptic flow compared to the oxygens. So if you don't use this ab initio, so this is basically calculation use these actual ab initio input from the low energy structure theory, where they can actually calculate the structure of these two line nuclei from first principles. If you just use Wu-Saxon distributions, you will essentially get this black curve, which is actually below 1. So you can see that this is a really easy big signals in the experiments that you can easily detect in heavy ion collisions. Try to see whether the modern initial input from light nuclei in the low energy physics plus hydrodynamics really works for these collision systems, or really or something else is done if the experiment agree with the other ones. So this is actually one of the really interesting opportunities that currently realized in the FCX setup, that you can actually probe both heavy ion collision and also ab initio nuclear structure physics in these heavy ion collision systems. Okay, so far, basically, we're still within some comfort zone that the colliding nuclei are not so small. But in the heavy ion collision, you can go extreme. So you can actually go to proton in one of the targets collide with ions. So just give you an idea, what does PA look like versus heavy ion collisions. So you can see that system evolves. In the heavy ion collisions, you have very large systems. And also for small systems, you only have about a very small, tiny part of the collision interaction zone. And the particle emitted per event also is significantly less compared to AA collisions. So they basically are in the same, correct the same scale. And you can see basically that the small system is really kind of produce a very small droplet. And it kind of challenged our picture of whether the system with so few particles produced still behave hydrodynamically as a fluid. So what's surprising is that if you look at the flow measurement of these proton-like collisions, this has been measured by these experiments. And you not only need a hydrodynamic theory to translate proton-like collisions into momentum space, but you also need a really eccentric proton as an initial state to actually achieve that larger value of V2. So if you start with a round proton, say a proton just like Gaussians, with some color charge fluctuation in the middle, and every event is really round, and then you get V2 is about 3 factor 3 less compared to experimental data. And only works that is some kind of, you have 3 hotspots that can have real fluctuation like this, that it generates a larger eccentric size of proton, shape of proton, then can give you such kind of measurements. So this actually challenges, these measurements not only challenge our understanding whether fluid element works, but also if fluid element works, you also require that proton shape to be really eccentric, that you can actually have the picture to be agree with the data. So in every aspect, this actually is a very challenging measurement, and we are still evolving in theory, trying to understand what is the real theoretical origin of this collective behavior in small systems. Is there any other information we can see from this small system to support whether this is a fluid or not? So one thing we can look at is that if this is a hot fluid generated as a small QGP drop, it will have black body radiation as well. So you will have thermal radiations from these systems. So what you can do is you can calculate collectivity on the left-hand side, and also photon radiation on the right-hand side. So if you introduce a thermal radiations, you will get this bump in the small kind of low PT regions compared to the calculation without this thermal component. And the yellow point is the current preliminary data from Phoenix, which has really large uncertainties. So at the current stage, both curves are compatible with measurements. But the data you can see is slightly prefer the one that has to include the thermal radiations. So what this study tells you is that by looking at both collective flow and maybe other real probes, that you can actually the combined measurements can actually help you to provide strong evidence whether there indeed is a strong coupled phase in these small systems or not. Now let's go one more step further, is basically look at, instead of proton-like collisions, in our field, there's also collisions you can trigger by so-called axial peripheral collisions. Because these two nuclei has really relativistic speed, they carry charges, so they will have really strong electric fields. So these photons can actually fluctuate into some hadronic states and collide with the other nuclei on the other side. So this means it's not even a proton, but some kind of virtual meson kind of collide with the hadronic objects. And this actually imposes another extreme in this setup to see whether small system conductivity still persists. And lo and behold, that if you measure these systems at the larger multiplicities, you also again get the non-zero elliptic flow with these solid red dots comparable with this open circle, which is the proton-like collisions. So if you run blindly, just say, okay, if a hydrogen even works with this kind of virtual photon calculations, you put in some essential ingredients, you find that, okay, the theory actually can give you a good quantitative descriptions of the electric flow for both gamma lead and proton. So this hydrogen picture seems even happen applicable even for these extreme challenging science conditions. So let me basically end my journey by basically telling you that, in the near upcoming, there's a lot of experimental upgrade programs coming. There's an upgrade from RIC to basically collect a lot of high real probes, measurements that can help us to do more precision physics. And also, we haven't talked about, but there's also other facility coming up to look at the phase structure of the QED and defining chemical potentials. The small system story is still ongoing because there's an EIC collider coming in the US, and we basically expect that this electron-ion collision as a small system, which also could wave in the small system stories as we go to the 2030 era. So that's basically my summary. So I hope to convince you that the Quark-Gluon Plasma in these extreme conditions that create heavy-ion collisions are really interesting object to study, because it's relativistic kinematics, strong coupled systems, and also exhibit universal collective behavior compared to other cold atom systems. In our field, we're entering a precision era in terms of that we can really use multi-messenger observables to actually study different aspects of heavy-ion collisions and verify our theoretical understanding of the systems. And our field is really approaching to use unified theory framework and then Bayesian analysis to extract the underlying physics in these multi-variable kind of settings. So I talk about the journey that our field has going through about 10 years in terms of studying small system collectivities. And I think along the way, we have certainly currently newly found that we build up connections with low-energy nuclear structure physics to use our initial input from their structure to do collectivity scan for QCD at different scale. And also these ultra peripheral collisions actually is a promising connection to the future EIC collider for the heavy-ion studies. So thanks.
Questions?
I do, but it's a specific question. Let's see if that substitute.
Yes, please.
So sure. On your slide 40, it's very interesting that yeah. So to some level, you're saying that by doing this ratio and looking at, for instance, collision with lead, the ratio to lead collision, and assuming that lead is like a sheet of paper that sort of gives you the ink, right? That's a great idea and all that. But why is it that if you assume a spherical wood saxon, the ratio becomes smaller than 1 for central collision?
Yeah. So if you assume both of the nuclei wood saxon, because there are 2 more nuclei in the neon, it's more round. It just has less fluctuation than oxygen. So then the ratio of V2 just becomes smaller for the bigger systems than the smaller system. And the ratio becomes smaller.
Because you have more fluctuation
in the oxygen, because you only have 16 nuclei in there. The shape is fluctuate more compared to the neon, which is 20.
So that's already considering fluctuation, but even because I'm guessing even the colored curves would be considering fluctuation, right? And
yeah, the color could also consider fluctuation and potentially some kind of structure like this bowling pin structure.
Right.
So that if you have a bowling pin structure, you will really have a larger elliptical shape for neon compared to the oxygen. But if you assume both the neon and oxygen just have standard Wood-Saxon deformation without input at beta 2, you will basically get a ratio below 1. But you can artificially put a beta 2 in there. That still will be larger.
Okay. Yeah. Okay.
I have a question.
Yes.
Since, I mean, you mentioned a lot about this Bayesian stuff.
Mhm.
Now, of course, it's this big. But then you talked about hydrodynamics in small systems.
Yeah.
Bayesian, despite what some people think, this Bayesian / machine learning stuff doesn't actually think for you. It sort of takes a model with lots of parameters and then searches efficiently in parameter space.
Yes.
But like, I mean, if you gave Ptolemaic data of the solar system to a Bayesian model, it would never have gotten Copernicus. It would have gotten a better Ptolemy. And you mentioned, hydrodynamics in small systems, which I kind of think are still not really understood on the basic level, because, for example, I mean, the Knudsen number is much bigger than 1, and fluctuations are humongous and stuff like that.
Yeah.
How sure are we that we know enough of the fundamental structure of the event that these Bayesian estimates are sort of reliable? You see what I mean?
Yeah, my take is, I agree. So the Bayesian analysis doesn't have a kind of false verification that your model is wrong. It can basically just tell you that if you want to assume your model is correct, it gives you a fit to the data. So basically, I think the philosophy, at least my philosophy, will be, I want to stay in some comfort zone that I only apply Bayesian analysis to the large system, where essentially, as you mentioned, if you check the Knudsen numbers and also the spatial gradients, they are small enough that you can justify the hydrodynamic kind of descriptions. And then you want to basically use the data or constraint to extrapolate to small system and see how basically the model is behaving in these extreme conditions. So when you push the model to its limit, or basically, I think what is hidden kind of in those calculations as you go to more and more peripheral collisions, as you're changing the parameters, the final outcome really sensitive to what your choice of the models. And those are basically needs to be factored into some kind of theoretical uncertainties in the calculations, which hasn't been done systematically in the calculations. All the calculations see in the small system basically just took one parameter and it works and it just fit to the data. But I think what in the future needs to be have a proper estimate of the theoretical uncertainties on that curve to really say that we have a good understanding of the small system or not.
Further questions?
So you had a presentation. I saw something on small systems such as PA and gamma.
Yeah.
What kind of collision system is that?
Yeah. So this is mean that these two they look at ultra peripherals that these nuclei and these nuclei just pass. They never touch. But because the nuclei carry charge, it has a strong electric field. Basically, can produce photons, and the photon can collide with the other nuclei. So what you find is that in this kind of ultra peripheral collisions, occasionally you will find a collision that with really large multiplicity produced, and this interpretation is that the virtual photon can fluctuate into a mesonic states like a rho meson, and the rho meson collide with the event. So that's kind of the real event, but this is the event that right now with the LHC you can pick up those interesting geometry and then study these type of collisions. They are really exotic collisions, but one of the extreme conditions that people experimentalists try to push the collective measurements into this level.
Further questions? Charles?
But that's very highly interesting because then we go to QED, right?
Yeah, you have a QED component.
Right, so we can actually calculate everything with high precision in QED. And then whatever is different will be from QCD, so it's a way to sort of like probe.
Yeah.
Right, I mean, tell me if you don't agree with me, but and that's why EIC is so interesting also.
So this is a way that the current experiments used as a way to connect to EIC before EIC come, because EIC is that you have a exact control on the kinematic momentum energy of the photon coming in by selecting the kinematic electrons. But for these UPZ ones, you don't have that connection, but you still have just this experimental setup. You have virtual photon hit the nucleus, but you don't have the control on the incoming momentum of the photon.
Further questions?
So am I to conclude from this that we can actually do a
Do
little
I
bit
know?
further events in
Yeah.
EIC?
Well, yeah, that's promising, but again, as Josh said, this is just challenging the whole theory of hydrodynamics and our understanding what is really going on here. So, you can run this simulation, but then not be the correct answer. But I think these are really kind of exciting areas that even in the EIC, you might see this collective behavior.
But if you go to any of my actually statistical physics colleagues, I have one sitting right there.
Yeah, you should think about Ken particle with statistical
Right,
mechanics.
right.
That's
We're
essentially
gonna go there, right? I mean,
Yes.
is hydrodynamic valid?
Yeah, but that's a challenging question. So in our field, it's challenging in different ways, but experimentally, you see evidence that this strongly coupled system still behaves like hydrogen.
Well, tell us how we can answer it.
Georgia answer, big answer.
Maybe I have an answer, yes. Further questions? Okay, if not, thank you very much. Be around today and tomorrow.